All right, I'd like to do now some example problems dealing with permutations, combinations, so forth. Okay? And here's our first problem. Imagine you have 6 trees to plant. You have an oak, a maple, a buckeye, an ash, and a poplar tree, and you're going to plant them all in one row. Well, how many different possible arrangements are there for the 6 trees in one row? Okay? We know that what we have to choose from are 6 trees, and we know that the action involved is planting the trees. So we have to plant 6 trees, so there are 6 actions, so there are 6 trials. So we will make 1, 2, 3, 4, 5, 6. 6 blanks, okay? And we know that according to the fundamental law of counting, that whatever numbers go in here, we are going to multiply them all together. Now, we have 2 questions to ask. Always these 2 questions. Number 1, once I have used one of my members to choose from, can I reuse it again? Applying that here, once I've planted a tree, can I use that same tree to plant someplace else? And of course, that's a stupid question. The answer, of course, is no. Okay? So that means we go on to the next question. And this question is, does the order of the trees matter? If I plant them in the order I've got here, oak, maple, buckeye, ash, poplar, is that really any different than poplar, ash, buckeye, maple, oak? And the answer is yeah, that's a different arrangement. And I think it's inherent in the problem to understand that, that would be a different arrangement. So I do want to count those. So since the answer to that one is yes, that means I am talking about a permutation. And we do permutations the following way. All right, how many members of my set to choose from do I have available? I have 6. Okay, now let's go on to the next. Now that I have taken one of those 6 and planted it here, how many are available for here? Well, the answer is 5. Over here, since I've planted 2, I now have 4 left, and on. This is 3 and 2 and 1. So this is 6 times 5 times 4 times 3 times 2 times 1, and hopefully you recognize that as being simply 6 factorial. And 6 factorial is one of the factorial function is one of the functions in your calculator. You can press and you find that that is equal to 720. Okay? If you want to use the NPR function in your calculator, since this is a permutation, we can just use NPR and go directly to the answer, realizing that we have 6 to choose from, and we're going to use all 6. So that is simply going to be 6 NPR 6. And if you enter that in your calculator, 6 NPR 6, you'll find it gives you an answer of 720. So I don't care which way you do it, if you use your calculator or if you just understand it on paper, the answer in either case, there are, believe it or not, 720 different possible combinations, different arrangements, I should say, of those 6 trees. I certainly wouldn't want to make a list of all of them. Okay, let's go to our next example. A family has 5 children. How many different arrangements of boys and girls are possible with those 5 children? Well, okay, first of all, I want to think, how many actions am I talking about? How many trials? Well, the fact there are 5 children means they have 5 children. So we have 5 blanks. 1, 2, 3, 4, 5. Okay? Now, what do we have to choose from? Well, we have either a boy or a girl. I have 2 elements in this set from which to choose. So question number 1, once I use a boy or a girl, am I allowed to reuse it? Well, that should be obvious here. I have to. If I only got 2 to choose from but 5 blanks to fill in, I'm obviously going to use them, right? Okay. So Here we go. We'll fill it out as we did before. I am allowed to reuse. So this is neither a permutation or a combination. How many different choices do I have for my first child? Well, it could be a boy or a girl. For my second child, how many choices to choose from? Well, it can be a boy or a girl. My third child, boy or girl. Boy or girl, boy or girl. This is simply just 1, 2, 3, 4, 5. So this is equivalent to 2 to the 5th power, which your calculator will quickly tell you is 32. There are 32 different arrangements in terms of boys and girls given 5 children. Okay? And hopefully, if you're not understanding, you can go back and back this up and re-go and go through and see if you can figure out after a couple times of seeing it. Let's continue anyway. Next example. Say you're playing checkers with a friend. Okay? You play 6 games of checkers, and you win 4 of those games. Well, how many ways is it possible to win 4 of the 6 games? One way would be to win, 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 and then lose, lose. Let me write that down. We could win, 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 lose, lose. Another possibility is to lose the first 2 but win the last. Another possibility to win 4 games is to win the first 2, lose the middle 2, and win the last 2. Let's do one more example. Another possibility is to win the first one, lose the second one, win the second, win the next one, whichever we are on, and win the last one, okay? Win, lose, win, win, lose, win. That's another possibility. Would you agree there are many, many, many? The question is, how many are there? How many different arrangements are there of this? Well, I'm playing 6 games, so there are 6 trials. 1, 2, 3, 4, 5, 6. Okay?